Good afternoon. Slide is visible?
Yes, sir.
Yes.
Yes.
Okay. So, what we were discussing the last class that about the decision boundary. Okay. So, what is decision boundary? What we have discussed that decision boundary is a basically if this is a kind of space and this is some sort of data points something. So decision boundary is just a very simplistic setting. This is the kind of. Now what we said that how we'll get it. Basically this is our hypothesis function. This is our hypothesis function that what we defined in time of our linear regression. If our hypothesis function is such that so and this is a parametric hypothesis, so it's a parametric function. Now this parametric function with some parameter theta like this. So these are the parameter theta. So and this x1 x2 is basically what x1 plus x2 if is this, that is x1 x2 in this way. And if we say that these settings, this particular settings is basically giving this particular settings, then we can say we predict y, the y is equal to 1, that means it is a positive logic. If this hypothesis function, so minus 3 because it is minus 3 here, plus x1 plus x2 is greater than is equal to 0. And y is equal to minus 1, sorry, y is equal to 0 or minus 1 if this minus 3 plus x1 plus x2 less than 0. So these are the two, this is the way this problem is basically defined. But if we say that can it be possible to find out some separator, then the equation of this separator is what? Minus 3 plus x1 plus x2 is equal to 0. Better to say it is not here, it is equal to 0. So greater than less than 0 equal to 0. So that what does this mean? X1 plus x2 is equal to 3. So this is the equation. So this is the equation of your separator. And this separator is called our decision boundary. Now this decision boundary is kind of this, we can say this is a kind of decision boundary, but that may not be a unique decision boundary or unique separator. We can get separator like this. We can get separators. So there is an infinite number of separator we can say. So that means given any two, you can say data set, we have a different kind of. And why only linear? We can get a nonlinear separator like this or nonlinear separator like this. It is also possible. So definitely this decision boundary is not defined on the data points. So that's why I say decision boundary is not a property of hypothesis function. Sorry, it's not a data set, but it is a or rather it is property of hypothesis function. So because your hypothesis function is basically going to drive are going to dictate the decision boundary. If your hypothesis function is different, your decision boundary is different. Okay, so this is the that we have discussed in the last class. So now the question is that now if this is the kind of setting, okay, now you see the decision boundary here with of higher polynomial. So with higher polynomial. So higher degree decision boundary. And yet this theta transpose, this hypothesis function, theta t is minus 1 0 0 1 minus 1 1, and these are x1 x2 x1 square. Square means this is a quadratic function, and x2 square. So if when y is equal to 1, if this function is greater than or equal to 0, so if this function is equal to, what is your decision boundary or equation of decision boundary is basically x1 square x2 square is greater than or equal to 1, or better to say is equal to 1. So that is the decision boundary. Yes, sorry. So it is basically a circle, equation of circle, equation of circle, and so your decision boundary is a circle. There's a small some problem there. It's looked like a kind of elliptic, but it's just imagine it's a circle. Again, the decision boundary not property of this function, because we can easily do the decision boundary in different way. Just for example, if you just adjoin these 2 points. Now you adjoin these 2 points. Now if I adjoin these 2 points. Sorry, this is the linear. So this may be another decision boundary. It's not circle. So it depends on the hypothesis function, how you define your hypothesis function. So it's a 4 straight line you can join, you can get. So obviously this is the depends on the hypothesis function. But this is a concept. The decision boundary concept is a very, very important in the case of classification. So now we are basically dealing with what is dealing with a discrete output or output values. Okay, and this kind is called classification. So now here come that this is another type of very important type of supervised learning setting. It's called classification. And as we say earlier, that this is, although this pictures is of a two-dimensional feature space, this is a 2D feature space, or you can say that is basically two-dimensional kind of thing, but the feature space may be multi-dimensional. And so what is multi-dimensional? That means one is for color, it's for texture, cost, and this color also may be 1 2 dimensional. So and so on. Shape. Then in the weight, something like that, and so on. So on. Okay. So these are the feature, and if this feature these are why it is red and blue, red and green. This is a this training samples is already labeled. So what is important? So what do you mean training of a classifier? Training of classifier finding a decision boundary. Now, decision boundary is such that if you give a novel new point here, okay, let's say this is apple and it is not apple. This space is left hand side not apple. So if we get a point here definitely we say this is the non-apple or not apple. But if a data point is fit here, we can say definitely this is an apple. Now, by virtue of which we are saying that by this decision boundary. If it is the left hand side, it's not apple. Right hand side is apple. Okay. So this is in any testing situation, we'll give any novel point or any novel this of the same dimension. Most probably is from the similar distribution. So we can take it. So given the right answer of each example of the data, the discrete number of outputs. So that's output is 2. It's a let's do output. It's called binary classification. Classifier by the output equal to 2. One is apple and non-apple. It may be multi-class classifier come later. What is multi-class classifier? Okay, so this is the just example of the classification. Okay, so now we discussed about linear regression. Now we have a simplistic setting of the classification. So classification is basically a two-step process. So first is model construction. What do you mean by model construction? It describes a set of predetermined class. So what are the things? Let me first just run through, just reading up. Each tuple or sample is assumed to belong to a predefined class, determine the class level. So it is very easy to understand because it's a class supervised setting. So there is a class. So these are the, let's say these are apple. That is basically said. And there is some sort of, these are not apples. So this basically same. So these classes have been given. The set of tuples used to model construction is training set. So these are the, basically these are the training set. And by virtue of this training set, we can find a classifier. This is a decision boundary. It's a line. It's a line. It's a straight line. And just please don't have my is hand. The writing is drawing is bit, yeah, but just it's a line. It's a line. It's a straight line that separate out these two. The model is represented as a classification rule, decision trees, mathematical formula. So here it's a basically a classification, or you can say it's a linear classification. So linear classification means there is a two things. The separator may be straight line or linear hyperplane. If it is a, let's say in general, I'm not saying in general, if there is a k dimensional feature points, generally our decision, the dimension of the decision boundary is k minus 1 dimension. You can say it's a two-dimensional feature space and your this separator is a single dimensional. It's a line, and that's the same thing. Okay. So the model uses for the classifying feature, or this is a basically this is called model construction, the training, and this is called model usage is called testing. Okay. So estimate accuracy of the model. The known level of the test sample is compared with the classified result from the model. And test set is independent of the training set. Otherwise, overfitting will occur. If the accuracy is acceptable, use the model is classified data tuples whose class levels are not known. So now there is a question that how to train. We come this question in a much more details in later part of this our um, study, this curriculum. But how to train means that we how to get to know the parameter of decision boundary. Now, the question is very easy because the decision boundary is, for our example, it's a straight line for your understand. Straight line. And what do we mean by straight line? That is parametric definition, y is equal to mx plus c, where m is a parameter. Number one is it. We see that it is a theta 0, theta 1, that m is equal to theta 0, it is, or let's say it's a theta 1 and it's a theta 0. So our decision boundary is basically a function of theta 0, theta 1. Or you can say for your understanding, of understanding, this is h. Because if you the h of theta 0, theta 1, this is your a of decision boundary. In case of linear regression, it is a hypothesis function. So h theta 0, theta 1 is your decision boundary. And this theta 0, theta 1 you have to know because these are the true parameters. So what do you mean by train? That training means by virtue of your samples, training samples, you can find out theta 0 or theta 1. That means m and c, so that we can line it. We can have more accurate decision. And we can, okay. So this is called training and this is called testing. Now actually after training, we can classify the novel and new data examples. Okay, so this is a basically two-step process. Here you can see some illustration is given. Now you see that this is the training sample. These are training samples. Attribute 1, which is and attribute 2, and class. There is a two class. One is no and one is yes. So two class, or you can say binary class. Okay. So there is a this yes attribute 1 and attribute 2. So attribute 1 yes large and 125k. So it's a three. You can say that it's a three-dimensional thing. One is active, active 1. This is active 2, and it is active 3. This kind of, and so somewhere it is basically here some data samples. Let's say first data sample is 1. Now this data sample is basically from here. It is a kind of this distance from this, and definitely this particular distance. These are data samples basically. These are the basic thing of these data samples actually. So it's just one data sample and something like that. Every data sample is there. So now we have to, now what is important that I can show here you, because if these are the all are three-dimensional point because of three. So here actually what happened, not a kind of this kind of plane is there. That plane is basically separating out. and this plane is basically here. It is a this plane. It's a it bit visually it's tough to say, but this is a plane that is separated out. If it's a linear, it's a linear plane. It's a nonlinear, it's a nonlinear hyperplane that is separating out these two things actually. Okay, so this is the idea. This is the thing. This is kind of this plane is basically differentiating these two. Okay, so this is the idea of that, and this parameter of this is a kind of plane equation, and that parameter is equal to maybe x1 x2, so theta 1 theta 2 x2 plus theta 3. So these are the basically theta 0 theta 1 theta 1 theta 0 theta 1 theta 2 is basically so theta 0 actually theta 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 3. These are the parameter set of the linear plane. Here it's a, since it's a linear kind of. And when we know these equations of this linear plane, now you apply any data points, we can find the it is either which side of this plane, that we can easily be understand, and accordingly we can say it is a yes or no. It's a no or yes for this. So this is called testing, and it's a training. Okay, so this is the basic idea. If you have any
Yes,
questions, you can ask. Yeah, please.
sir, in the training step, it was written that the test set and training data set should be independent of each other. What does that mean, sir?
That means that the training samples, whoever is the training samples, just for example, you are given for sense, let's say that is the object, that image classification or object detection kind of. Now object means it's a cat. So you given let's say you can say 100 images of cats, you given for training. Okay, now these 100 images, now this is a this image, this is a training sample. So, but here in case of testing you gave a new cat image that not belongs to training sample, that I am saying.
Yes, sir, got it, sir. Thank you, sir.
So this is the way of the classification test. Okay, now we have a very important discussion about loss function. Now this loss function we already understand in case of linear regression. What is this? Loss function is that now let's say this is our kind of linear regression, what we're doing. And these are our points. Okay. So what is our loss function there? What we have defined that our predicted point correspond to this point is this, and this point supposed to be this, but we get this. So there is a some sort of I am changing the color so you understand properly. You see, the loss is this. So the loss is this. Loss is this. And corresponding point loss is this. Okay, so loss function is what? Loss function is this difference. For each point, there is a noise of for you, because this is your hypothesis function, and this hypothesis function must should be touch upon these points. That is the ideal case. But your hypothesis function is you have plotted such a way that there is a certain loss. Okay, certain noise is there. We are failed to. That means, so this function, if you find this function at in the case of your linear regression, we use least square function. So it's a squared loss. You can say the squared loss. How to measure square loss? We said that this predicted point, so predicted point is y, is basically h theta xi, and the actual point is yi. So what is the difference? H theta xi minus yi. Take algebraic this sum and we take a square root of this. And this thing we sum up is equal to 1 to m, where m is equal to training number of training sample. Okay, so that was our thing. And what we have to go, we are arg mean of this. We have to minimize this function, so we get a particular function that is much more optimized with respect to the training samples. Now, here there are typically two steps involved in learning hypothesis function. As you know that how. First, we select the type of patient. Now, here one important thing. Now, before coming to the loss function, first of all, we choose the type of hypothesis function. Here, one can say that this type of this hypothesis function is linear in nature. So there is an assumption that in this case, this is a linear hypothesis function. So this assumption is basically this. So it constrained. So I think you recall one thing. We said that there is no free lunch theorem, that every hypothesis function or this every has a kind of assumption. So this assumption is linearity assumption. So this make a set of hypothesis function. Okay. First, we select a type of machine learning algorithm that we think appropriate for this particular learning algorithm. Maybe we say let's say linear regression or logistic regression. And assumption is, what is that? Assumption is basically that it's a linear. So this defines a hypothesis class H as a set of function we can possibly learn. So a set of function what? So whatever our hyperplane or straight line, whatever, it's a linear in nature. This is one important assumption. The second step is to find the best function within this H. Now, H is what? H is basically, we come all these things very detailed in our something class. What is that? Some theoretical aspect. This H is there. H is basically hypothesis class. Okay, this H. And our hypothesis function H belongs to this H. Okay. Now there is you can see there is a different kind of function. There is a different kind of function possible. And which of this similar type hypothesis function, what we're going to choose, it driven by this. and this function is called loss function. So the second step, find the best function with this. This second is actual learning process, and often but not always involves optimization problem, because this is optimization problem that we have seen. This is the optimization problem. Essentially, we try to find the function h within the hypothesis class that makes the fewest mistake. And we said the fewest mistake within our training data. Now, this is the one way to find the fewest mistakes. This particular optimization function is only one way to find out the fewest mistake. Okay. If there is not a single function, we typically try to choose the simplest by some notion of the simplicity, but we'll cover this. So basically, this kind of thing, this particular point will come later. This is basically this thing. This is how the simplest but accurate. So one thing is important: simplest but accurate. That is important. That we are trying to find out simplest function, but the accuracy is um, accuracy is okay. We got say of a sufficient accuracy, we can say. So how can we find the best function? For this, we need to some way to evaluate what it means. One function is better than another, and this is where the loss function, Rick's function comes in. So this is the optimization function. We can get the best function among the hypothesis class as a hypothesis function. So a loss function evaluates h, this h on our training data, and tells us how bad it is. So actually, this is basically a badness measurement of this hypothesis function. So if it is high, then so just forget out arguing part. So badness means minimum bad is a good. Minimum bad, the smallest bad is the highest good, in that way. So if this function is basically, if you just are not arguing this, that this function is basically the measurement of badness of this hypothesis function. So if you have any doubt, you can ask. So perfect prediction. It is a common practice to normalize the loss by the total number of training samples. That's why we sorry, one thing I missed. Before argument, there is a 1 by 2m because of this number. So it's a normalization training samples n, so that the output can be interpreted as average loss per sample. So this is generally we use a 1 by 2m, where 2 is a normalization function, so 1 by 2 m is number of class. That's why. Okay. So that we understand what is meant by loss function, because loss function we generally encountered very important in our case of machine learning. Now it is makes lot of sense for the deep learning. So any questions in this slide? Fine. So there is a different loss function. So different examples or different loss function is there. So 0, 1 loss, it's a very easy to understand. That means the simplest loss function is 0, 1 lot. It literally counts that how many mistakes are there. Okay, that's one apple, non-apple. This is. Now you will say that is apple is query, this is query, and this is prediction. So apple ही तुम दिए हो और ये predict भी apple कर रहा है, so it is +1 or 1, yeah, +1, 0, 1 loss. apple दे रहे हो, ये इसको नो apple बोल रहा है, so it is a false negative, so 0. नो apple दिए हो, इसको apple बोल रहा है, A false positive 0 and no apple दिए हो इसको no apple बोल रहा है is a true negative plus 1. So this is the way the 0 1 loss is basically this. These are the losses. Sorry, I give you this. If it is a loss, if it is a loss, you can. This is the apple. Apple बोल रहा है. So loss is 0, and these are the loss is 1 because this is a loss, na? This is a 0. The loss function is the same, just conventionally this. So it literally counts how many mistakes an hypothesis function H makes on the training set. For every single example, it suffer a loss of 1 if it meets in mispredicted and 0 otherwise. Exactly what we said. So basically, you can say in this way, you can write here in this way that true positive is 0, true negative is also 0, false positive 1 and false negative is also 1. So it's the loss actually. Loss. So it's a negative sense. So इसमें loss ज़्यादा हो रहा है, इसमें loss कम हो रहा है. The normalized 0 1 loss return the fraction of misclassified training samples, but also offer effect to a training error. Okay? So they can easily understand. 0 1 loss is often used to evaluate the classifier in multi-class binary classification. Settings are rarely useful for guide optimization procedure because the function is non-differentiable and non-continuous. Definitely you can understand it's a discrete function. Formally, the 0 1 loss can be stated as in this way. That's what I actually said that. So if it is not equal to y, it is 1, and if it is a y is equal to 0. Loss function returns the error rate of this dataset D, and for every example that the classifier misclassifies, its loss is 1 and suffered, whereas the correctly classified sample is 0. The same thing what I actually said that. Okay, so this is the loss function, 0 1 loss. Squared loss, better not to, because we already say that this is exactly that hypothesis function is theta of xi minus yhi, and it is taken the square of this is square, and there is a some sort of over this I is equal to 1 to n, where n is equal to each your training samples, number of training samples, and it's a normalized trend over here. So this is the square loss. The square the two effect, the loss suffered to always a non-negative because it's a non-negative. It's a squared function, so it's a non-negative. Non-negative, and loss suffered grows quadratically with the absolute miss. So it's a quadratic function. You can understand it's a square function. So it is grows quadratically. The latter property encourages no prediction to be really far off, or penalties would be a solar. The different hypothesis function is likely. So that is very easy to understand because it basically increase the loss, right, in a quadratic fashion. So if there is a big loss, it grows quadratically. Okay. Now, flip side, if the prediction is very close to correct, the square will be tiny and little attention will give into example to obtain the zero error. But you can understand this is zero, the square loss will be even smaller. That if it is this particular loss function is generally called delta x or delta L if this is equal to 0.00001. So it's square of this. You can this square of this is 11.00001. So it's very tiny. If given input x, the level wise probabilistic according to some distribution this, then optimal prediction minimize the squared loss is predicted by this. Actually, this is very formally squared loss is this. So this is squared loss. We know it very well. And another thing is absolute loss. Absolute loss is basically this. It's a algebraic difference. Is theta xi minus yi. And this is algebraic difference. It's a mod function that is suffered penalties because the suffered loss grows linearly, but it grows linearly. So that is important. It's grows linearly. So if given input x, the level y probabilistic according to some distribution p of x, optimal prediction is basically absolute loss is predicted median value, kind of so. So it's basically median of this, and this is absolute loss. Okay. So before summarize, we just want to, before going to the mathematical formulation of logistic regression, there is a very important concept we just try to introduce, because this is the one of the major issue that we'll going to cover in a very details, in a very elaborative way, that is called generalization. So, and the question I'll give you the way. Maybe this is a bit complicated to understand it here. Now let's say what we have said. This kind of points are here, and what we have seen that this is our linear function, and what we said, that these are the corresponding losses, these are the corresponding losses, and we want to minimize these losses that we have been shown in the last slide. Now the question that, okay, this is a kind of uh, hypothesis function, and there is a, now question is that how much accurate we really want, how much accurate we can say hypothesis function we really want. This is very important. So what does this mean? Now previously our assumption is this. Okay, now we can say no, we are our assumption, we bit, you can say, relax. So we say no, we have some sort of curve, you can say, the our linear function, hypothesis function, may be a non-linear. So if we say that our function is like this, okay, now if we can this, our squared loss is very close to zero. If you're not understanding, please ask. If this kind of just situation, if this kind of thing is a squared loss, that is very good. Correct or not? It is correct. Okay. Now let's say situation. This situation that we are going for this kind of thing. If a situation where we have a point, let's say here, okay, and this point is basically, you can say, a noise. If we go by this formulation or this thing, so our hypothesis function will be like this, something like this. Let's say something that. Now the question is that which hypothesis function you want to choose. So the question is that which hypothesis function you want to choose. Because look, it's a noise, but you're understanding that we are going to point all the points, because you a priori don't know which point is noisy point, which point is very. So the idea in this case that let again I write this kind of function here. Let's say this. We are trying to find out. Let's say we have a. This is a. It's a not linear. It's a non-linear. But we ignore this point. For you can say called that it's for beta generalization. Generalization. What does this mean? This curve is going consisting for most of the point. And if some point is abruptly different, we are not going to consider it by virtue of the generalization. So you can say this point is not somewhat obeying the data distribution when the most of the data obeying. Okay, so we consider maybe it's a valid point, but you can say it's maybe a noise, but it's outlier kind of thing. Okay, we don't know. So if we don't know about this kind of thing, so with that we, so it basically going to consisting with or is a synchronized with the most of the data point for the sake of the generalization. So a big part of the machine learning focus on the question how to do the minimization efficiently. If we find a function h, how to lose your data d, how do you know whether it's still examples right and not in d? So that exactly the same thing what we said, that this point, maybe it's a kind of arbitrarily different point, or it may be noise. So we always go for this, the major distribution follow. So generally what happens, we'll see and in next course of our study in this machine learning. So what it will give, if we go by this idea of generalization, that the generally we said the testing data or novel data with supposed to not in the in training sample, it generally follow the similar distribution. So maybe if you consider this, the training noise is very less. Noise is very less by virtue of that we point every point we have considered. But the testing noise will be generally abruptly low. And you know, everybody we know this is one of the major problem called overfitting. That we'll discuss. So this is a very important issue in machine learning. I'll get back in later. Okay. So this is very important to understand. Okay, we'll stop today. Thank you for listening.